saw that, or in the last few classes, we have seen that Lagrangian is basically a function of generalized coordinate and time, right? So when we consider the Lagrangian to be a function of generalized coordinate and time, okay, we do understand that the generalized velocity that we talk about, that is qj dot, comes in automatically, right? Because it's basically a function of time. So when we talk about the generalized velocity, it basically appears explicitly, but a time derivative of generalized coordinates. Okay, these are time derivatives of generalized coordinates, and so we call them as dependent variables. The entire aim of Hamiltonian is to remove this dependency and bring in an independent variable, and that is why we include that. Okay, so we also say that in Lagrange's formalism, if you consider a single particle in configuration space, so if you have the x-axis, the y-axis, the z-axis, that will actually define the position of the particle. Okay, or in other words, you can know at what instant of time where the particle is, but then you cannot really trace a path. Okay, so if you basically draw a graph, if you have a particle here, and at some point the particle was here, so let's say at time t1 the particle was here, okay, and at time t2 the particle was here. So you cannot really say whether the particle followed this path to come here, whether the particle followed this path to come here, or whether the particle followed this path to come here. You cannot judge that based on Lagrangian, not possible. But Hamiltonian tells me the path of the particle also. Okay, that is one of the fundamental difference. Okay, that is. So if we go back to Hamiltonian, we know it is actually used to remove the dependent variable and introduce a new independent variable, and this independent variable is called the generalized momentum Pj. Okay. So we are getting rid of Qj dot, we are including Pj. Now you know, when you know the momentum, which also has got a velocity, but then if you know the momentum, you know how fast it is going, right? And what is the amount of mass that it is carrying, and so on. So it gives you additional information. Okay, not just the velocity, it gives you additional information, and then you can predict the path also, so you can know along which path it is going to follow. But that is why Hamiltonian is important. So when we say Lagrangian, L is qj dot and t, but when we talk about Hamiltonian, it is qj, pj and t. So Hamiltonian is a function of generalized coordinate, generalized momenta and time. Okay. So let's try to remember this, okay, because this is important. And the path followed that it takes is more important. This is what I am going to discuss now. So this is something which you are going to come across again and again, and I think this we have already derived. If you remember, in the first few classes, in the first unit, we said that Pj is nothing but the generalized momentum, right? Because you know L is equal to T minus V, and then V is equal to mgh, does not depend on velocity, so this part will become 0, right? This part will become 0. So del L del qj dot can be written as del T del qj dot. Okay, and T is nothing but half m, let's say qj dot square, okay, or half mv square. Okay, and then you can actually differentiate it, and you will see that the final result that comes from here is going to be nothing but mx dot. You can put the values and you can see that you are going to get mx dot. So that is going to be momentum, and that is why it is called the generalized momentum. So this is we have already derived. Okay, so don't get confused that I have written this all of a sudden. We have already derived it before. Okay, so please have a look at the last class. So this is your generalized momenta, and this is included in the Hamiltonian, and this actually gives me more information compared to only the generalized velocity. So if you consider single generalized coordinate, let's say along the x-axis, there is only one component of generalized momentum. Okay, so if you consider three generalized coordinate, you will have three generalized momentum. So you will know what is the motion along the x-axis, along the y-axis, and along the z-axis. Okay, so you will know the motion along x-axis, y-axis, z-axis, and then if you analyze it, okay, you make a computer program to actually plot it and try to understand it, you will see that what path that particle follows, and that is why generalized momenta is important. Okay, one more term that we actually came across in the previous section was phase space, but now I'm going to explain phase space a bit more, okay, because This is going to be important when we are talking about the Hamiltonian. Okay. So phase space is something which is much better than configuration space. So whatever concept you had till date, okay, whatever you have studied in your undergraduate level, okay, you might have come across the term phase space, but then the essence and the importance is far greater. What happens is that configuration space only talks about a particular position at any instant of time, as in Lagrangian, but phase space will give you more information. Okay, so if you consider n dimensions, it means that it also includes the dimensions of momentum. Okay, in which direction it's moving, what's its velocity, and all those information can be extracted from there. Okay, so what happens is when momenta and coordinates are given equal status, so that means coordinates and momenta are both equally important. Okay, both are equally important. So it's not that you consider coordinates and then you say that okay, momenta is not important. It's not that, right? Both of them are considered equally, and based on this a space is designed. Okay, and if that space is designed using the momenta and coordinate system, we usually don't call that as configuration space. We don't call that as configuration space. That is phase space. So for your exam purpose, if I'm asking you a definition or uh, an understanding of phase space, probably this slide gives you the answer. Okay. So what happens is the path by the system for describing the motion. Okay, for describing the motion, please understand this: motion should be there, otherwise momentum doesn't make much of a sense. Okay, needs a space represented by 6n dimension. Now you will ask me why 6n. Okay, so what happens is if there are n number of particles, there will be 3n coordinates plus the momentum coordinate. Okay, so you basically have a 6n dimensions. Okay, so for each particle there will be 3 momentum coordinates, 3 position coordinates, it will be 6. If there are n particles, it will be 6n dimension, and that is why it is 6n dimension. The concept is simple. Okay, the concept is simple. When you read a book also on classical mechanics, you have to concentrate on what is being taught, and then you will understand better. Okay, so each particle has got 3 coordinates and 3 momenta, and this space is called the phase space. So if someone asks you that what is the difference between phase space and configuration space, I think you can answer it very convincingly now. Okay, so configuration space is something which you have studied till now, but now you understand that whenever I have a gas molecule and I want to understand its motion within a cylinder, let's say, or within a closed enclosure, the gas molecules will move in different paths. It will collide and then it will keep on moving here and there. Okay, how do I understand that? So that understanding first comes from phase space. So phase space is a term which we are also going to use again and again in statistical mechanics. Okay, so statistical mechanics we are going to use it. So this is very relevant. And here we are saying that the path of that single gas molecule within the box or within the enclosure can be explained in phase space and not configuration space. Okay, so that is why phase space is important. Okay, and not configuration space only. So what are the advantages of Hamiltonian? So I think now it is very clear to all of us. Even if I don't give you this slide, you can write down at least 2 or 3 advantages. Okay, so if we list it down, there are infinite number of possible paths through any point in configuration space. Okay, so if we have just a configuration space, there are infinite number of possible paths. I don't know from which path it is going to come, how it is going to follow that path, and so on. So these 3 coordinates will basically provide the position but not the path. Okay, but then when we consider the 3 coordinate and the 3 momentum coordinate, by definition the state of the system is complete. The entire configuration of the system is known to me now. Okay, and that is why this momenta coordinate is important. Okay, so when you write down your notes, if you're writing it down now, I think this is okay. I can just do it fast. Okay, else you can always get back to the video. So what we usually do, or how we actually design a Hamiltonian, is this. What we do is we actually specify some initial value of Qj and Pj. Mind you, we are dealing with Qj and Pj now, and not Qj dot and Pj dot. Okay, it's Qj means generalized coordinate, Pj means generalized momentum. at any instant of the path. And if we are able to specify what is the momentum and the generalized coordinate at any instant, we will be able to fix the whole path of the moving system. So this gives me the liberty to predict the future along which path it's going to follow. Mind you, this momentum should not change. Okay, if it keeps on changing at every point, then it becomes again unpredictable. It becomes a chaotic system. Okay, but then I'm considering that the momentum is fixed. Okay, then I can definitely say what will be the path. Okay, so we can only say this if we are actually considering a phase space and not the configuration space. So when we consider, see, something is arbitrary, right? So you are finished your undergraduation, you want to take, you applied for, let's say, NIT Nagaland, you applied for Nagaland University, okay, and so on. So you apply in different places. At that time, you are arbitrary, right? You are not very sure where you are going to take your admission. But once you take your admission, you are fixed. You've decided, right? So when we talk about this configuration space, I think you are there in configuration space. But once you have taken the admission, you are in phase space now. You basically have a path, okay? You basically have a decision made, okay? And that's why there is no arbitrariness involved in phase space. The arbitrariness is less. The answer is less. It is not perfect, obviously, okay? And the answer is less arbitrariness. It's more perfect than configuration space, because it might happen that next year you get admission into a different, let's say, an IIT. You might go to that IIT. So there is less arbitrariness, but then still there is some arbitrariness. Okay? Possibilities are there. So this is what is the understanding of Hamiltonian point of view. It's from a theoretical point of view, and I think these last 3-4 slides are more of theory. Okay, and what we are going to do next is we are going to understand the variational principle of least action. Okay, but then since the number of students are less today, so I think I should not continue. Okay, I'll keep this as short as possible, because did anyone add? Okay, 9 are there. So, but still, okay, I can take then might be one more slide I can take. Okay, 9 of you are here, so I think you've joined a bit late, but I think you've got caught up with whatever I've said till now. Okay, so now we are actually going to a bit of mathematical derivation, and we are talking about Hamilton's principle. Okay, and we have got the variational principle of least action. So for your exam purpose, you might be asked to state Hamilton's principle or state variational principle of least action. For your entrance exam also, they do give you this, and then give you 4 options where they will actually give you the solution to these. Okay, and then you have to take the correct answer. So the variational principle is this. Okay, this is the variational principle, and you know the delta represents a very small change, arbitrary. Okay, it's basically infinitesimal change. Okay, and then T by V is nothing minus but the Lagrangian. Okay, so this is basically called the variational principle. So you look into this, the difference between the kinetic energy and the potential energy, okay, over a range of time is very small or almost zero. Okay, almost zero, and this is what is called the variational principle. So if I just give you this simple integration, you should be able to predict what should be the statement. Okay, but we're going to come to that statement anyhow. So this is usually denoted as delta I. Okay, and then it is delta of, and T minus V is nothing but L Lagrangian into dt. So this is 0. So that means over a period of time T1 to T2, the variation between the kinetic energy and the potential energy is negligible or 0. That is why it is called the variational principle. Okay, simple concept of maths. Okay, not very complicated. So if we just read this through, okay, let me just read this. States the motion is such that the integral of the difference between the kinetic energy and the potential energy is stationary for the actual path. So now you see this actual path. The term is actual path. Actual path. Do I know it from configuration space of Lagrangian? The answer is no. Do I know it from Hamiltonian? Yes. And that's why we are using it in Hamilton's principle. Okay, and then it says that the integral of the difference, so you can look into it. Okay, you can make your statement. Okay, I think this is very simple. You basically take the integral, okay, integral of the difference between the kinetic energy and the potential energy. And if you consider it over a period of time, it is basically stationary. So that means there is no change. Okay. So if you consider at instant of time, let's say t1, and measure t minus v, okay, and then there is some kind of value you get, okay, there will be a small change, but there will be a value which you get, and then you measure at that t minus v at another instant t2, you will see that that variation will more or less be similar, okay, it's similar, it's not going to change much, and that is why it is variational principle, okay, least action. So the motion is such that the integral of the difference between the kinetic energy and the potential energy is stationary for the actual path. So this is what is important, okay. So as I said, I think I should correct myself here. As I said, it is not always mandatory that the kinetic energy and the potential energy difference will be zero. So that might not happen all the time, okay, although it does happen, okay, because if you consider a system, let's say I will consider a pendulum system, and if you consider at certain point of motion, you will see that the kinetic energy and the potential energy are same. So in that kind of system it might happen, okay, but then this is not always mandatory. If you generalize it more, we say that there might be a difference, but that difference remains the same throughout the motion of the path, okay, it's not going to change much, okay? And that is what is the essence of variational principle is important. So that's Hamilton's principle or variational principle of least action, okay?